So yes, you might guess that I'm coming from a humanities background. Kevin Du asked me to talk about digital humanities in OCR, so I'm wearing a sport coat. But Kevin isn't here to appreciate that, but hopefully some of you will be interested in what I have to say. And amongst the motivations for the kinds of things that we do, you might peruse The Economist back issues back to 1871, as one does, and then an article on English public opinion on the war, by which they mean the Franco-Prussian War. Some of the philosophers should turn their attention from the subject of spectroscopic investigations and the invention of electrometers, galvanometers, hygrometers, and so forth, to the far more difficult problem of inventing a mode of measuring the intensity and diffusion of political wishes and convictions. Okay, so that's what we're doing. Maybe they just wanted somebody to invent public opinion polling. I don't know. But I'd like to think that they wanted us to invent the kind of research communities that we're building around the computational social sciences and digital humanities. And, if you read the literature on how, bureaucracies shape society, on how states form, right, a lot of it is around data, right? The kinds of breadcrumbs that we leave behind us in the kinds of societies that we've built for ourselves. And I don't have to convince people here of the potential of data for good or ill. But the right, sort of rising up from the chthonic depths there. But he's playing poker, so he's living his best life. The sociological point here, right, is that we have big data because, well, first we live in an era of big government and big business and big science. These organizations that capture data as a way of doing business. We live, in worlds where our social lives have been put online and are thus legible to data in a way that, James C. Scott believes that, people flee into the hills in Southeast Asia to get away from. Because we are in a process of recovering and digitizing our past in a way of turning, wood pulp into data, right? So, so I'm going to focus in this talk mostly on these sort of historical questions, not, our social lives online today. And the way to think about, turning, this wood pulp and linen rags into data is one that the humanities have been trying to do for the past 20 years, say. And the methodological turn in the humanities, or the one weird trick that you might have to turn the humanities into data, Comic Sans, I learned that from Jason, is that you bring together skills in an atelier that haven't been put together before. Right, and so the argument is that there was a point of when a lot of things were being put into print in the Renaissance that you bring together all these different trades, whether it's a goldsmith like Gutenberg or somebody else, and they would all be working together in an environment that they hadn't been working together before. And the person that you might pay attention to is this learned-looking fellow in the glasses on the right. He is the editor, who's a profession that didn't exist before. And this is the person who's reconciling texts, who's choosing texts, who's organizing data. And what I want to guard, this is what we want to produce. But that's not necessarily the self-presentation of a lot of people who are putting historical data and humanities online. Consider what the Internet Archive views as what they do. Right? This is a picture of, they're proud of their big book scanning device, and there's just a person there, perhaps saliently, just a woman who's the servant of this machine, and they're just going to industrially digitize things. And that's not how I see this ecology of computation and the humanities and data in our work. I see it this way, right? We have documents in various languages, and there are a lot of people working on building representations. Right? A lot of people in this room building representations for various kinds of text, various kinds of languages. And how can we do that in some way that accurately reflects the necessary information in those documents? how can we infer the structure that connects all these different representations? You might call it the relational structure, network data, as well as all of the structured data grammars that people learn in computational linguistics. And then how can the models that we build for doing representation and relational structure perhaps allow us to perform new tasks, build new classifiers to solve other problems, to add more structure to the data as we have it. Okay, so that's all very high level, and so let's talk about something much more concrete, like the Affordable Care Act or healthcare. Right? So according to legislative historians in the Library of Congress, this is how Obamacare turned into law. Right? It would be a lot longer song than, I'm just a bill, right? Because you have all these complicated things going on, like there was a bill introduced in the Senate to provide low-interest home loans to veterans, and then the entire text of that bill was deleted and had some completely different text inserted into it. And there was some parallel stuff going on in the House, and there are all these bills that get reconciled and then passed by both chambers without the reconciliation process because Ted Kennedy died. So this is all very complicated, but that's nowhere near the whole story. This is just the complete bills that went into the Affordable Care Act. There's lots of other stuff like this. This bill originally wasn't in this picture. This was just, a little standalone bill that some particular member had been trying to get passed to provide accommodations for breastfeeding mothers in the workplace. And, this is now in the Affordable Care Act because this individual provision somewhere along the line was inserted into it. Or to take another example, right, here is where some text from a failed 2005 bill to control the previous drug panic of methamphetamines got inserted into the successful 2005 Patriot Act reauthorization. Right, so this isn't science. Nobody gets a citation for having come up with this great idea for controlling meth. They just get their policy ideas advanced. Perhaps they vote against the bill. Right, and so if you consider this kind of textual analysis, right, we're doing good old-fashioned textual criticism. We're building up trees for how texts evolve over time, as here, right, different kinds of language for imposing sanctions on Sudan get incorporated into language for imposing sanctions on Iran. Right. And, so a question.
Yeah, so there's I'm curious what the weights on the edges mean. Is that the probability that an edge is there, or is it the amount of text that was sucked down? Fraction of text that was sucked down?
Right, it's the fraction. This is just the raw fraction of text that was sucked down.
Is there a distinction between provisions that have been moved as opposed to templates that have been copied and adapted for one purpose?
Yeah, that's right. That's a good question. So ideally, you'd like to learn those distinctions from data jointly. In the work that we've done, we simply got some labeled data for boilerplate copying versus legislative idea copying, and actually a 6-category scheme that political scientists who are less lazy than we are, went through and did some labeling. But yes, particularly this sort of foreground-background distinction is the kind of thing that you'd like to just learn from the data itself. It doesn't seem that hard, and so we have some initial results on that. Right. Consider another example of information propagating through a looser and bit more open system. When somebody publishes a paper in Proceedings of the National Academy of Sciences, you may be surprised as computer scientists to learn that it isn't your university's press office that puts out a release about it. Commercial journals have their own press offices which put out releases about these things. In other fields, computer science is under-resourced in this respect, right? And so, and things like Eureka Alert get read by science journalists everywhere, and then science journalists write various stories about these ideas, and they propagate through the whole system, from more scientific publications like Scientific American to The Guardian to, I didn't know that land grabbing wasn't an Italian word. They had to borrow the English one there. But right, it's about the same paper. Or, consider another even wider lens on information propagation with my colleagues Maxim Romanov and Sarah Svant, looking at the propagation of ideas in biographies of Islamic scholars spread throughout time and space in a great extent. Okay. So those are all the kinds of examples of how this inference of network structure from textual evidence might be interesting to the humanities and social sciences. Let's look a little bit more at one case that we've done a lot of work on over the past 5 years, and that's a viral text project, which is a collaboration at Northeastern between people in computer science and people in English and history. What I'll be showing you is about propagation within the English language media in the US and other English-speaking countries. We're now starting a project on propagation of information in the press in many different languages with colleagues in Mexico and Europe. Okay, so 19th century newspapers. Why should you care? 19th century newspapers were complicated objects, right? They're an all-purpose medium that contained not just news, but poetry by John Greenleaf Whittier, and, humorous stories and advertisements and scientific news and all kinds of things. And the key thing here is that no librarian is going to go in and catalog the metadata for these individual poems that get reprinted in 19th century newspapers, right? And even if they did catalog them, right, the titles wouldn't match, the authors wouldn't match. This poem's interesting because it's by Charles Mackay, who's most famous these days for having written Extraordinary Popular Delusions in the Madness of Crowds. And this is he was a Scottish newspaper editor. Newspapers in particular, from a social science perspective, provide a lens for a great geographical swath of the US in particular, and a great temporal swath. And it's interesting to know how, in the age of print, somebody might put together something as, big as a newspaper every day. Well, if you look at this picture of, in Harper's Weekly from 1874 of a farmer trying to pay his newspaper subscription with some, a virtual still life of pumpkins and game, you'll see on the dubious editors, behind the dubious editor, a pair of scissors and some columns that he's clipped out of other newspapers, right? So if you're trying to build a model, there's the selection process of cutting out bits of other newspapers. And then there's another noisy channel sitting in the room behind it, a bearded compositor, setting up the rest of the newspaper in type. So we have a couple of interesting computational problems here. One is the low-level problem of just figuring out what bits of text have been copied from one newspaper to another, and how those texts that differ due to errors in composition or selection might cluster together. And, it's a computational problem, beyond just building a model, because we have a retrieval problem. If in just the US we have 63 million newspaper issues in the 19th century, we don't want to do the 2 quadrillion pairwise alignments that, at 1 second of alignment per page of a few hundred words would take a few million years. Right. And the alignment problem isn't as simple as others that we might solve in natural language processing, right? Because, the piece of text that's copied has unknown boundaries, right? And so there's some aligned region, and then by hypothesis, there are some unaligned regions around that. And furthermore, as Jason pointed out before, there's going to be different kinds of copying processes going on. There's going to be less interesting boilerplate or mastheads, manifestos, advertisements, the legal boilerplate in bills, and so forth. Right. And finally, we're dealing with text given to us by the Library of Congress that looks like this. Right. So you'll just have to trust me. It's about Henry Clay. Right. So why is even this low-level task of identifying reprints, clustering reprints, an interesting problem for NLP people to work on? Well, people have worked on sort of subtasks of this in the past, right? Sort of partial duplicate detection, plagiarism detection, doing local alignment. Yuri Leskovic and his group have done a lot of work on what they call meme tracking, but there they simplified the problem of identifying the boundaries of the text by just looking for things that were between quotation marks. Right? And so we've got a problem where there are no known boundaries, where the text could be arbitrarily long, which could help us but also hurt us computationally, where we want to ignore reprinting among certain kinds of close documents and look for more unusual things, and where we have very noisy OCR. So, for instance, a lot of the fingerprinting techniques that get you the big efficiency gains in plagiarism detection are going to break down. And so what we'd like to produce and what we do produce from this process are both pairwise alignments, cases of two different versions of this language on breastfeeding in the workplace, as well as larger clusters, right? All of these different versions of, for instance, James Buchanan's last concern trolling State of the Union speech, right? If only you'd listen to me, you wouldn't have these problems. Or, all of these different versions, with bad OCR of, a story by popular temperance writer T.S. Author. And what we find, it's interesting to literary historians and historians by looking at 19th century newspapers, right, is it's not just, hard news or politics, right, speeches and telegraphic news, right, and the newspaper is very interested in the completion of the transatlantic telegraph, but also sentimental stories, about parents and children or husbands and wives. Travel narratives, a journey through the sewers of Paris, which was taken by a correspondent for a Swedish journal. It's mostly fiction. The Swedish journal mentioned doesn't actually exist. Or, jokes about, the evergreen topics, families and so forth. Lots and lots of poetry. And from point of view of textual criticism, right, there are going to be interesting differences in the various repeats of these texts, which will help us to reconstruct the flow. And that something's become really popular and viral when, parodies start getting posted of it. Right? So we can view things not just at the level of individual texts, but where the repeated material shows up on the newspaper page. So you can see sort of high-level strategies for where repeated material gets put. The evolution of a front page that has less repeated stuff and more new hard news, for instance, by the 1880s in this paper. Or just the relative improvement in communication speeds over the course of the middle of the 19th century. So all of this historical stuff will be in a forthcoming book. We need to have a manuscript done for the press by the end of this summer. So sort of this will have a historical focus, but it will also talk about the computational methods. Okay. So, from the point of view of a literary scholar, right, I've given you a story about texts, popular texts, mutations of text, and so forth. A social scientist, of course, might be interested in textual data because they give you evidence about social connections among people, or you have all these people, they're talking to each other, but unlike a lot of work on social media where the platform itself tells you what the links are, we would have to infer what the links are to do interesting social science with it. So I'm going to talk a little bit about some network models that we've developed. Yeah.
Sorry if I'm not sure I understood. So all the frame that discussed so far is because the final objective is somehow to represent, to store all this paper, archive, or documents into some system. And whether you want to store them significantly or to have some meaningful representation, let's say embedding. So that's all your point. That's your final objective, right?
Right. Well, you might be. Well, let me put it this way. You might be interested in different intermediate points in that cycle, right? Maybe you're interested in just the relational structure itself, right? Which texts were popular, right? Sort of a heavy hitters problem. I give you a big corpus. You tell me which texts were popular. Or how do I get a representation of documents in multiple languages so that I can compare the documents in multiple languages and talk about that.
It's just
right.
Storing.
Right. Okay. So let's talk about this network inference and propagation problem. Right? So if we look at a schematic view of, the 19th century U.S., right, there's some cities, and information is going to flow from one place to the other. Perhaps it's, something happening in Washington, it's propagating out from there, south to Richmond, north to Philadelphia, New York, to Wheeling, West Virginia, which is important because it's, where the National Road, now I-70, Pulaski Highway going out of Baltimore, meets the Ohio River, and there to the western parts. And, sometimes you'll even get news flowing back from St. Louis to Philadelphia if, there's a story in Philadelphia about the reaction of people in other parts of the country to the news from Washington. Right. Okay. So what are some ways that social scientists, at least, have thought about information propagation in political networks before? Yes?
How good are the date stamps on the documents? When
So,
you're using the arrows, you're making use of when you're drawing these arrows, you're making use of date stamps, right?
That's right. So I'll be concretely talking about newspapers in this example where we have date stamps that are accurate to the day, right? And so yes, there's some ambiguity, right?
People have trouble getting those back. Somebody's typed them in for you.
Yes, those as metadata, except for the Bavarian State Library that for some reason failed to tell us the dates of their newspapers. But yes. Right, and yeah, so the different kinds of granularity of date stamps might allow you to do different things. So I'll be talking about some, blog data later where you have, granularity that's much finer, of course, than a daily newspaper or let alone a weekly newspaper or monthly magazine, right? But this will be important, so hang on to that thought, right? And so social scientists have thought about problems of predicting the importance of nodes or predicting the existence of strong links between actors in a social network or political parties or other things, using some fairly simple methods, right? So, casting this as a link prediction problem. People in computer science have done this as well, right? Given what we know about the text that existed at these nodes, can we predict whether there's a strong direct link between two particular nodes in the graph? And, they might, basically, they run a bunch of regressions between all pairs, and they test whether the network is important by doing a permutation test. In models of social media, people, have done things that are a little bit more complex, come up with parametric models for the waiting times between a piece of information arriving at one node in the network and a piece of information arriving at another node in the network, right? These are often inspired by work in epidemiology. All of the ex-physicists who work in network science like these kinds of models, as well, again, as Yuri Leskovic and his group and Matt Lease and other people like that, right? So can we just come up with a simple parametric waiting times model for when nodes get particular information? Or if, like Michael Kearns, you're in a business school and you're interested in marketing, you might be interested in where, who are these social media influencers, where should I, who should I give my product to, or who should I pay off, who has a lot of Twitter followers, as we just found out, so that they can maximize the spread of information throughout a network, right? And people have done this kind of work. Right, and we've done some work of this kind, right? There's sort of this pairwise regression kinds of models allow us to find out that in the 19th century, the Republican Party, which is new at the time, the mid-19th century, is much more cohesive than the Whig or Democratic parties, right? The Republicans are much more likely to repeat Republican stuff. I know this is not yesterday's news. This is the 1850s, but it's true, right? That there's a much more cohesive political party here, and also there are very strong locality effects. The same state effect is in fact stronger than raw geographic distance, right? Because if you think about, say, Memphis, Tennessee, which is closer to St. Louis than to the state capital in Nashville, Memphis is still going to have a lot of stuff about state politics and state issues, right? Which overwhelm the geographic closeness. And if you control for this stuff, other kinds of social movements like anti-secession papers or anti-slavery papers are less important. Right? But if we want to build a model that incorporates this kind of text and doesn't necessarily require in very fine-grained timing information and arrival time information, what could we do? So Hopkins is a good place to talk about this because it's somewhat similar work here. Let's unroll the graph that I showed you a couple of slides ago. Yeah. Mm-hmm.
You suppose that if you were to sort of stratify, I guess what I'm thinking is that slavery or anti-slavery.
Right.
It's a bunch of other stuff too.
Right.
That, is sort of irrelevant to the slavery question. Is there a way to sort of control?
Control for the story, yeah, you're quite right. That would be an interesting thing to do. And part of the problem is that doing genre classification is something that we're in the midst of, and I can't give you some results on that. I guess what I would say is that from the point of view of how an editor of an anti-slavery or any other paper might make up his paper with that pair of scissors, right? He's only going to do exchanges of a few papers. Right, he's not going to subscribe to 100 different papers. Actually, there's an interesting regression discontinuity study to be done because in 1843, it was no longer free for newspaper editors to have other newspapers delivered to them through the mail. They had to pay postage. So, you might see an interesting discontinuity at that date, as well as other interesting regression discontinuity is when new railroads or telegraph lines go in. Right. Yeah. Okay. But looking at the differential effect of genre might also be important, although then there's an interesting thing about genre in that they have different speeds, right? So political news, you just need to get there faster, whereas poetry can travel more slowly. Okay, so let's unroll this network that I showed you a couple of slides ago, right? We'll start in DC on Monday, and we propagate out from there. And so now we can have repeats, right? If you get a story in Philadelphia on Tuesday, but then you get it on reflux from St. Louis on Friday. Right? And now you can kind of see what's coming, right? Now, if we assume simple contagion, which for this kind of news propagation we can, right? It doesn't have to be a DAG where like somebody's intensively collating two manuscripts to produce their own manuscript. We can assume a simple contagion model here. So everybody has a single parent. And if we unroll things in time, arrows can only point forward in time. Then, as you might suspect, we have a directed spanning tree over the particular issues of papers as unrolled in time like this. Right? And we could have edge features like the source and the target of an edge, the particular time lag between a parent and child, the text edit model, and so forth. Right? And it's no secret that although there are an exponential number of possible trees, I could use this 10-year-old slide to tell you that we have combinatorial optimization methods for summing over all possible trees, right? Sum over all possible trees using the Tut's directed version of Kirchhoff's matrix tree theorem. Right? Took him 100 years after Kirchhoff, right, to prove this version. Right. Okay. So we can do that. Right, and if we knew what some, yes?
How useful is the date line information, the date and tested source of the in the book?
Right, so right, how useful, so we're going to treat it as if it's accurate to the day.
Embedded as opposed to the date of newspaper.
Oh, sorry, the date line information. Okay, sorry. Yeah, the date line information in the newspaper is mostly non-existent in the 19th century. Right, there might be discursive descriptions of a ship that left Hamburg on April 7th tells us that blah 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 or something. We're not trying to do that, although you can imagine doing that in some cases. Or our correspondent said on Wednesday. Yeah.
When did that New York Times style?
Right, I mean that came out of telegraphic bureaus. And one interesting thing that people ask us is, hey, the telegraph, the transatlantic cable was laid in, or the one that actually didn't break was laid in 1867, right? Does the whole composition of these newspapers change then? And you don't get this kind of organic propagation of information through the system. And the answer is it changed for only a few things, right? It was really, really expensive. So you could get very brief telegraphic notices of particular events or financial information. It's how Reuters made his money in the Crimean War. But there's still the vast majority of these papers were being populated by slower propagation mechanisms. Yes.
Do you see an effect, just following up on that, do you see an effect of old news being less likely to propagate?
It's right again. The confound is this genre effect, right, is that there's some things which keep their value even if they're old, right? So that would be an interesting question, right? Is that, are there things that sort of have, that decay slowly enough that you can see them being reprinted less, right? So part of the problem is these sort of telegraphic news, right? It either propagates within a week or never. And there is a bimodal distribution in log space. If you look at the log lag between, the first newspaper to repeat some story in the last newspaper, right? There's a lot of stuff that happens less than 14 days, but then there's another peak that's like 6 months, right? And you can sort of there's some nice experimental cases, right, where you get Hawaii, right? Doesn't have a telegraph, you have ships getting there, and right. Anyway, okay, so if we were lucky enough to convince some historians and literary scholars to write down trees like this for us, right, here's how the story about the transatlantic cable propagated. Here's how, John Greenleaf Whittier's The Huskers propagated. We might be able to train a model, right, that just maximized the likelihood of the trees that historians had given to us, right? But while they might be interested in doing that for 10 stories or 20 stories, or that they want to use for their article, they're not going to annotate a lot of trees for us, so that we can do supervised training. So instead, we're going to use something that sort of looks like a contrastive objective. We're going to maximize the likelihoods of the scores of the trees satisfying certain constraints given to us by the data, over the sum of the scores of all possible trees over these nodes, right? And what we'll do specifically is that numerator will be all the set of constrained trees that don't violate the dates that we observe, right? So it might be possible that Richmond and Wheeling are copying from each other. That will be a tree that's allowed in the numerator, but a tree where Nashville is the source for Richmond will not be a tree that's allowed in that numerator if we're using time constraints, right? You could think of other constraints as well, right? Constraints that arise from the text or something. Okay, so we would like to get more data from the historians of 19th century newspapers to evaluate this. We don't yet have that, so let's flip to another data set, like the ICIE WSM blog data, right? We could, we might think we could use something like Twitter. Part of the problem there is that the network is always observed, and so that's not as interesting of a case, right? Here we have blogs where people are linking to each other, but they're also copying substantial amounts of text, and they're copying in a way that isn't just, made mechanical by the platform, right? So we have a bunch of posts. They have hyperlinks to each other, so, the arrow in this direction means that post hyperlinks to that post, right? And what we'll call cascades are these connected components of posts. And the ICWSM dataset gives us about 22,000 cascades that have between 5 and 100 posts. We throw out cascades that have more than 100 posts as being pathological. It's not that many, and then gives us a total of 205,000 posts. Okay. We also, in some conditions, will simplify the data in making it more tree structured, right? So this does have a DAG structure. This post hyperlinks to different previous posts. And so we'll also construct a version of the data set that throws out documents with multiple hyperlinks. We've already done boilerplate removal, so that's not as many as you would think. We still get 20,000 cascades with 500 posts for 202,000 total posts. Right. So there's so if we're interested in modeling information cascades, a natural question is, are we really studying, all of the same kind of object? So a lot of people, such as Sherrod Goel at Stanford, right, have pointed out, and Duncan Watts, have pointed out that a lot of what people call viral online is simple popularity driven by ranking algorithms, right? A YouTube viral video that lots of people watched because YouTube keeps recommending it to them is going to have a propagation structure that looks like this, right? There's YouTube, and then there's all the people linking to that YouTube or watching that YouTube video. When people talk about virality, right, they mean this multi-hop, much deeper tree. And in the data that they studied in this paper, something, they found a lot of popularity. In our case, we found like 84% of the cascades look like this, right? Popularity effect and not true virality on the right.
And of the remaining 16%, are many of them close to that?
Yeah, many of them are fairly close, but we'll see that in what the different kinds of models do with this data. Yeah. Right. And so that means that in a lot of cases, right, inferring the information propagation is really easy, right? You just link everybody to the first instance. So what we're going to do to make the problem harder is to group together all of the cascades on the same day, to turn them into a full forest. So now your job is to reconstruct all of these links if you didn't observe any of the directed arrows there. Right. And that gives us 938 cascades, 938 days of data in the ICWSM data set. Okay. So how well do we do with this model? So if we had separate cascades, right, the cascades that were these connected components in the hyperlink graph, we can do okay. How well is that, right? And if we just use basic features that previous models that built, parametric waiting time models of cascades used, just the identity of the parent and child and the time lag between them, you get about 62% F1 of, getting everybody their current parent and connections to root. If we allow additional features like actually looking at the text of the blog posts, then we could get 95% F1. But since the cascades are separate, a lot of them are fairly simple, and a simple attach first baseline is quite accurate. Okay. If, however, we use the merged cascades, where all the cascades on the same day are put together and we need to reconstruct the link structure between them, it's a lot harder, certainly with the basic features. You only get 4% F1. If you use the enhanced model that looks at text, you can get 25% F measure. The attached first baseline is no good, right? So we're doing a lot better than that. And interestingly, if we used a supervised model, right? So this is the unsupervised model that's trained with this contrastive objective. If we actually had the true trees, we still couldn't do that well. So the unsupervised model with the additional features and the contrastive training is doing a lot better. But if you give the supervised model access to all those extra features, it can do a lot better than that. But still, this unsupervised model that doesn't know anything about what cascades would look like other than preserving temporal ordering is getting about half of supervised performance. Now, well, one thing about this slide is that we're actually inferring individual links in cascades and reconstructing them. Part of the and we've done this sort of internal evaluation. None of the previous work actually evaluates this way. Not only, because it's hard, but because their models didn't even admit this kind of inference on their data. So to compare fairly to previous work, we need to aggregate our cascade level predictions into what other people have done in predicting networks. And basically where every blog becomes a node in the network. So now you have this, full general network. It's no longer a tree or a DAG. And our methods still do much better than, the previous a couple of state-of-the-art baseline models, of which we're representing one here in green. And we're evaluating it for each day as previous work has done, such as the, work done on parametric models. So the recall precision and average precision, if you treat this as a ranking problem, are much higher. So, we started by being interested in 19th century newspapers. We're still working on that, presented some results on blog data, but this is an area where I'd be particularly interested in hearing about some things that other people might be doing, because, we need more data to work on problems like this and to figure out what kinds of models are good.
So is the idea that you're working on the raw text and using the hyperlinks as the gold annotation? So
yes, that's right.
With respect to that.
That's right.
You're saying it's not actually gold.
It is gold, but right. Blogs lie about their sources. Right. For instance, you can find 2 Spanish blog posts that are very similar to each other, but only cite the original English news article. They were clearly influencing each other, but just as in science, right, you cite the important paper and not the less important paper that you got the idea from. Right. Okay. So we started by talking about network propagation among, texts in the same language. But obviously information flows across languages. Edgar Allan Poe kicked off French decadent poetry. We can, read biographies of Alexander von Humboldt in multiple languages, although, watch out that, right, it's in 3 volumes in German and 2 volumes in English, so it's not a one-to-one correspondence among the books. David Urowski and Charles Schaefer had this idea, almost 20 years ago, that the temporal information also told you something, right? That if you're trying to estimate Serbian English translation models looking at the time series data for nezavisnost and independence and nezavisnost and freedom might tell you that, there's a big spike around when certain former Yugoslav republics declared their independence, which is not quite the same thing as freedom. Right? And so if we have this kind of time series data, all the news on May 1st in English and German, all the news on May 2nd in English and German, perhaps that could provide us some sort of signal. Right? And to bootstrap these models, within each day, without any parallel data at all, we could start by simply looking for the faux or perhaps vrais amis, right? The words that look exactly the same in 2 languages. And it turns out that's, not terrible. Right? We can do document-level translation detection in many language pairs across script boundaries just by looking at matching tokens. Right? English Bulgarian, English Greek. Right? And in Newswire, right, there's going to be a lot of proper names. It's going to be numbers. Although, right, you are vulnerable to the house style of the UN, where this Arabic English problem performs a lot worse than an Arabic English Newswire document translation detection problem. But once we're able to bootstrap the system using this document level data, then we can start building a pipeline over this time series of 10 years of news. Right? We can compare documents, compare things at the document level to find things which might be topically similar, align them at the sentence level, and use them to train a polylingual topic model to get inferences about all of the vocabulary that didn't get picked up by this overlapping token bootstrapping heuristic. Just briefly, polylingual topic models were the sort of simplest possible extension to latent Dirichlet allocation. We came up with about 10 years ago, including Jason Narodowski there, right? That topics are now a set of distributions on words, 1 distribution per topic per language, right? And now documents are tuples where 1 or more texts could be observed in each tuple, right? So some documents are monolingual, so you only observe text in English. Some documents are multilingual, and so on, right? And it scales linearly with a number of languages, right? We're not estimating all pairs of models. And we can compare text in different languages by comparing points in the probability simplex of topic distributions, right? So that if I gave you, for instance, this English document at the top, Washington Urgent, Treasury Chief defends dollar, blah, 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 you would like to retrieve things that are, that have low Hellinger distance, which turns out, if you take the square root of all the probabilities, is a good approximation to KL, to Jensen-Shannon distance. You want to get things with low Hellinger distance like this, and not things with high Hellinger distance like that. Okay, so what we're interested in is information flow. For now, what we could evaluate is machine translation. So we did some experiments where if we had some clean, the clean WMT training sets for news and Europarl, our test bleu on an English-Spanish task would be, the sort of baseline results in WMT, 23.75% bleu, a little bit better, right? The Europarl data is about 10 times as large, and this is a news test set. Just using the clean data, no sentences extracted from comparable corpora. If, however, we just use the data that we extracted from comparable corpora, from GigaWord documents over 10 years, and we have no clean parallel data, we can do even better at this baseline WMT task. And the slightly good news is that these things kind of compose, they never compose, linearly as much as you like, right? You could use both the news data and the GigaWord data and get a little bit better, and the Europarl data and the GigaWord data and get a little bit better than that. Okay. So yes.
Is it obvious how to tell what the comparable are? So in the GigaWord, do they say this is comparable?
So the only signal we're using for comparability is, again, date. Right. So and as you say, right, there may be some slack in the date, right? Like the story appears tomorrow in the Chinese press about something that happened in the U.S. today, or vice versa. We're ignoring all of those possibilities. We're just binning things by date. Okay. So for the final thing that I'm talking about, and Jason did have a lengthy introduction, so I'll give myself another 5 minutes. But right, is to go back from these very high level views of networks or comparable data and go back down into inferences about the text itself. So recall. We've been talking about newspapers, which, in the Library of Congress's interface look like this, but in the text behind them look like that. But we're going to use information of a kind that I've already shown you. We're going to use the fact that we have multiple different, and we're able to find multiple different versions of poetry, like this, something that a textual critic might be interested in. And we're going to use the fact that also newspapers were set up in type, and a lot of them were left in type from one day to the next. If somebody paid for this ad to run for a week, they didn't bother to, unset the ad and reset it again the next day. So there's going to be a lot of literal boilerplate from one issue of a newspaper to the next. Both kinds of copying. Okay. But in order to tell, so the Library of Congress can't tell you how good their OCR is, but we can. But because we can take scans from the Library of Congress that look like this, from the Richmond Dispatch, and find other corpora that have been cleanly transcribed, in this case, the University of Richmond, randomly selected some newspapers between 1860 and 1865, just randomly selected dates, and produced transcriptions that look like this. They clobbered all the line breaks, unfortunately, but that's okay because the line breaks are still in the OCR output. And so we can do a forced alignment to get, both possible supervised training data if you want to use supervised training data as well as evaluation data. Similarly, people have transcribed a lot of old books by hand, so there are data sets called Early English Books Online, EBO, and 18th Century Collections Online, ECHO, which are big microfilm sets that your library here pays far too much to rent every year from the Redex Corporation. However, there's some public domain manual transcriptions of a few thousand texts in those collections that we can then align to public domain books in the Internet Archive. And we can get a data structure that looks like this. Right, so if you look at that second line up there, opening of the Cordillera discharges itself, right? This is the Internet Archive's OCR transcription of that line of text. And we've aligned it with the Text Creation Partnership, TCP's manual transcription of that line of text. And, you have problems like this long S, the origin of the integral sign being confusable with F and so forth. But so in addition to pairs of correct and OCR text, we also have all of these other witnesses to that very same text, right? And some of them have obviously different editions, right? In this edition, the line break is between the and Cordillera, so it's clearly not, the same copy, right? They've retypeset it with different line breaks. And in this case, there are like 20 other witnesses to this text. And what that means is we now have a data set from two different sources, two different, both in English, from this Richmond Dispatch corpus and the EBO Echo TCP corpus, where we have manual transcriptions for 2.1 million lines of newspapers and 8.5 million lines of pre-1800 books. of which 43% of the manually transcribed lines are also observed in some other data set in the Library of Congress. And 64% of the lines in those manually transcribed books are also observed in some other book in the Internet Archive. So we have this huge collation of these databases, not only that nobody has created before, but we also collate them with manual transcription so that we can evaluate this whole system. I mean, it's interesting how these things are differently skewed, right? Like there are many, even though a smaller proportion is duplicated in the newspaper, when it's duplicated, it's really, really duplicated because it's like an ad that's run for a week or a really, really popular news article or something like that. Whereas, most of the duplicate witnesses in the books are like doubletons or something. Okay. So what are we going to do with this data structure that I showed you on the previous slide, where we have all of these different OCR versions of a text, optical character recognition versions of a text, right? It's like a multi-sequence alignment problem, right? We have all these different sequences, and we want to line them all up, but this is exponential in the number of witnesses. Okay. So think about how, these days we go about building transducers from noisy text to clean text. These days, you're probably using some kind of encoder-decoder model with attention, right? You're feeding characters in, getting some internal representation, passing that representation forward, and inputting the characters from your decode so far into the decoder. Plus, you're maintaining some distribution over positions in the input, your attention mechanism to figure out what parts of the input you ought to be decoding at that particular time. But now we're trying to decode multiple documents simultaneously. This is a problem that's sort of like multiple document summarization. And, multi-doc summarization is still trying to come up with good attention mechanisms for dealing with longer and longer inputs. One thing that has been done for short document summarization is simply to concatenate all of the input documents together, and then in the decoding portion of your machine, figure out which portions, which of the inputs it should be paying attention to. That kind of makes sense for summarization, right? You can only summarize one part of the document at once, although, there are other summarization tasks that you would maybe prefer to summarize several different input documents at once. Half of the people think that this restaurant is terrible when it comes to service. A third of the people think that the tacos are good. Right, so we could concatenate them. I mean, this just gets computationally bad as well. Some people have thought about, sampling high quality or particularly representative inputs when doing multi-document summarization. But as is often the story in language technology, a stupid system combination turns out to do a lot better. Right? If we just encode each of the inputs independently, and then combine the attention vectors over those inputs with a simple average, we can do a lot better. And note, you might say, hey, but wait a minute, some of those witnesses are actually kind of good, and some of them are kind of cruddy, and maybe we should learn weights over the different witnesses. As in a lot of different system combination tasks, that doesn't appear to help. Just averaging does better. Okay, so what does this mean? It means that baseline OCR character error rates and word error rates for newspapers and books are about, range from 14 to 8% error character error rate, 35 to 19% word error rate in the raw text as compared to the manual transcription. If we just learned a supervised encoder-decoder model to go from dirty OCR to clean manual transcriptions, we can improve that a lot. If we use the extra witnesses and concatenated them together like they do in multi-doc summarization, we can possibly improve a little bit in newspapers, but we actually get a bit worse for books. Whereas if we average the attention vectors, we can do better across the board on both corpora and both error metrics. And if you do beam search, you get the 100 best, you get a nice Oracle headroom as well. Okay. So that implies that if you're going to build an OCR correction system for, 18th century books or 19th century newspapers, you should get some data to train your supervised model. But that's kind of an unsatisfying story, right? You need to get data for this particular typeface or these particular kinds of errors, and the error distributions error distributions are going to differ greatly. So can we do without all of that expensive training data? Well, we'd prefer to do without expensive training data. And we'd also prefer not to train our multi-input decoders on multiple inputs, right? Like, if you have a machine translation system, you don't want to always have multiple possible outputs whenever you're training a model that takes advantage of that. The number of witnesses is going to vary from line to line. We don't want to bake that structure into the model. So we'd like just to train on single input-output pairs, and we'd like to not train on supervised data. Okay, so our baseline is going to be the original OCR output again. But if we consider that we have multiple witnesses, another baseline might just be select the witness that has the best score under the language model. But that gives us an idea. In addition to just supervised training on the OCR manual pairs, we could do unsupervised training on the, randomly selecting one witness to be the input and select the best under the language model witness to be the output. Or we can just, have a synthetic uniform error model entirely and synthesize all of our data. Take some clean text and then synthesize dirty text without looking at OCR output at all. Okay, so here's our baseline on the test corpus where we have not only all of the lines with multiple witnesses, but all the lines, one or multiple witnesses. And so you'll see the error rates are higher here, right? The lines that had multiple witnesses just naturally are, closer to the consensus anyway, right? So the baseline error rate is in fact higher here. If we just select for those lines that have multiple witnesses, if we select the best witness under a language model, we can improve. Not all lines have multiple witnesses, so we just have to select the baseline in those cases, right? So that's still the same data set. If we train a supervised model, it's not quite as good, right, because it's a harder problem, right? If we train a model using the best witness under the language model, we can, we're not doing as well as supervised, but we're improving across both baselines across the board. If we just train using synthetic data, that turns out to be actually a little bit, worse across the board, right? We're just training we're just randomly generating the inputs, and then we give it actual OCR data. So maybe we can refine that model a little bit by one round of bootstrapping. So after training this synthetic model, do some self-training. And this is particularly nice because this gives us an improvement for books, which is good because if we just select the best witness by the language model, books are going to kill us. Because books have all those long S's, which will never be observed in any of the witnesses. Whereas if we if we uniformly generate synthetic data from a distribution, we can stick the long S in there, right, and get some improvements. Okay, so a little bit over the hour, but so apologize for people for leaving. But I've told you 3 different projects that occur at the different stages of the life cycle of digital humanities and computational social science, right? Sort of unsupervised learning for information cascades. It's all about, being interested in the relational structure for its own sake. Topics for, using topic models for comparable documents, about learning better representations that then allowed us to do other things. And using this relational structure to learn better OCR correction models, learning how to collate. I'd like to thank my colleagues, particularly Ryan Cordell, a professor in English, my co-author on the viral text stuff, as well as my students Ray Dong and Xiaobin Xu, and my former student Kriste Kerskovsky, who's now a postdoc at Columbia. Thank you. Sorry for talking so fast, because philology is the art of reading slowly. Right. I mean, you could put a language model. I mean, if you had a consensus model like the, Eisner and Paul transducer-based model, they could have then, intersected a language model with their lattices as well. But that's then another computation problem. Yeah. No, we have done some comparisons to more exact methods. Part of the problem is that our lines are just too long. I mean, it's like 40 characters or 50 characters, but at least in our implementation, it just like failed to run out of memory or do something like that. And yes, we could go in and try and really engineer those solutions so we could do a fair comparison, but we couldn't really. Yes.
Have you thought at all about looking at the borrowing back all the way to OCR, where we borrow, where the actual fonts borrow from one another, the strokes that people use are copied or adapted?
Yeah, that's right. So, basically, an interesting composition of two different Taylor Kirkpatrick papers would be he's done work on compositor attribution, right? But mostly with regard to the amount of white space between characters in his generative character models. What you'd like to be able to do, right, is actually say if certain, subparts of characters are shared, maybe between fonts, but that's not so interesting. Between different hands in a paleographic task, right? But you want to merge that with the ability to do the collation, so you can figure out what parts of the text are aligned to what other parts of the text. Yeah.
Okay, well, let's thank David again.
Thank you.